Welcome back to 15-Minute Math. So we just covered the fundamental theorems of calculus, both the first and the second. And those guys are real time savers because now that we know the fundamental theorem, we don't have to waste all our time doing Riemann sums and taking limits where the rectangles go off to infinity and all that hassle. We all know that that's a pain. Nobody likes to do it. So with the fundamental theorem of calculus, we can really start developing some shortcut methods to get around doing that. And really, that was the heart of what Newton and Leibniz really wanted to do when they were both kind of independently developing their version of calculus. They were really looking for ways to kind of shortcut what people used to have really clever, intuitive geometric arguments to do. And in fact, the word calculus kind of derives from calculate, or at least, a lot of similarities with the word calculate. They were looking for ways to calculate these sorts of things without appealing to geometric arguments, or without appealing to, without having to be the world's most intuitive mathematician out there. So right here we're getting down to really what Newton and Leibniz were all about, kind of deriving some ways to shortcut some of these problems. So remember that basically, summarizing here, the fundamental theorems of calculus just say that derivatives are the inverse of integrals. Those two things are, opposites in a way, kind of in the same way that squares and square roots are inverses, or exponents and logarithms. They're opposites. And so if I want to come up with an antiderivative, what that means is I want to come up with an expression. So this is going to let us, by the fundamental theorem, find these integrals a lot quicker. If we know the antiderivative, we can just apply the fundamental theorem of calculus, and then we can get whatever integral that we like. So let's start with polynomials. Typically, polynomials are the easiest functions to deal with in a calculus class, and we're going to start with just something really simple and hopefully build from there. So let's say we started with just x squared, and we wanted to find the antiderivative of x squared, which is to say we want to find an expression that when we take the derivative of it, we get x squared. Okay? And so maybe first of all, we should think about, just generically speaking, how we would take the derivative of and I'll go off to the side here. I have some polynomial, I don't know, x to the fourth minus 4x squared plus 5x minus 1. And let's say I took the derivative of that with respect to x, of course. I would just apply the power rule, right, for each individual term. So this 4 moves down, and then I subtract 1 from the 4. The 2 moves down and, of course, multiplies the coefficient. And then I subtract 1 from 2. Pretend there's a 1 there. The 1 moves down, multiplies the coefficient, and then I have x to the 0. And then we could pretend there's an x to the 0 there, and then the 0 goes down, and of course anything multiplied by 0 is 0, and so that term goes away. And then of course x to the 0 is just 1. Anything to the 0 power is just 1, so that's just 5 times 1. And so there we have our derivative. That's old news, but it's really nice to think about, very explicitly how we take a derivative. First, we move the exponent down and make it a coefficient, and then we subtract 1 from the exponent. So to find an antiderivative, we're just going to do the opposite of that. So hopefully it stands to reason if we move the exponent down and then subtract 1, we would, to find an antiderivative, add 1 to the exponent, take that new result, and then move it down. But instead of multiplying by that new coefficient, I suppose, we would divide by that. So x squared, if I want to find the antiderivative, well, first I would add 1 to the exponent, which would give me x cubed. Then that 3 moves down here, but instead of multiplying by 3, I want to divide by 3. Or another way to say that is I just multiply by 1/3. And so that is the antiderivative of x squared. And you don't have to take my word for it. Remember what we said that, quote unquote definition of an antiderivative was. It's an expression that when we take the derivative of it, we get what we started with. So let's just take the derivative of this and see if we get back what we started with. So if I took the derivative, first the 3 moves down, and 3 times 1/3 is just 1, so I'm not going to write that. And then you subtract 1, so you just get x squared, which is exactly what we started with. So 1/3 x cubed is our antiderivative. And remember, integrals work term by term the same way that derivatives do, or the same way that a summation would. And so if I had a larger polynomial, I guess I should say that was our first example. Let's do a larger polynomial here. And by larger, I just mean more terms. But also it's going to have a higher degree. So let's do x cubed minus 4x squared plus 9x minus 11. So we're going to do the antiderivative of this, but we're just going to do it term by term. Okay, and so first thing we're going to do is we'll add 1 to the exponent. So let's start with here. Add 1 to the exponent, which will give me x to the 4. Then that comes down, but don't multiply. We divide, or multiply by the reciprocal, I suppose you could say. So that would be the antiderivative there. And then for the x squared, now we're over here, add 1 to the exponent. That would give me x cubed. Move the 3 down, but you don't divide, or I'm sorry, you don't multiply, you would divide. So it's going to be 4 times 1/3. Again, I'm multiplying by the reciprocal, or you could just think about it as, okay, the 4 was the coefficient already there. I'm just going to divide by my new exponent. Then I'm going to have, same deal here, x to the 1. Well, that goes up to 2. And then we're going to divide by our new exponent. And then we have x to the 0. Well, you add 1 to that, and you have x to the 1. And then divide by 1, I suppose. So there we go. Now, here's where we probably should stop and think about kind of a hidden fact here. So I'm going to delete all my annotations there. So when we think about antiderivatives, we kind of want to think about this as the original function and this as the result of a differentiation process. Okay, so when I'm handed an expression and somebody says, okay, find the antiderivative of this, I'm thinking to myself, okay, this thing in the black box, that was the result of a differentiation process. What was the original function? That's really what I'm asking myself. And the answer is we don't really know for sure. Like what you see in red definitely is a possibility. But also notice that, what if I would have had a constant on the end of this? What if this would have been like plus 10? If I would differentiate this, wouldn't I still get what was in the black box? Because remember, constants drop off anyway when you differentiate. So I could have also had plus 22. I could have had minus 7. I could have had minus pi. Any constant goes away. Like, it will not show up after we differentiate. It's impossible to tell if there was a constant there or not. Like, if I would just do the antiderivative process, which I usually call the power rule because it kind of is just the inverse of the power rule. So if I do this sort of power rule for antiderivatives, I get what I have in red, but that's not the whole story. Or at least it doesn't have to be. There might have been a constant there that I didn't know about. And so it's kind of just the common practice that we put plus C here to stand for some constant that may or may not have been there. And what happens is this generates then a family of all the possible functions that could have produced that derivative. And when we say we're going to find the antiderivative, that's kind of what we're after. We're kind of after all the possible functions that could have satisfied that. So up here, when we were first introducing the concept, I didn't want to necessarily get into it, but now that we have talked about it, let's slap a plus C on here. So this is really our antiderivative. It's all the possible functions that could have given you a derivative of x squared. right? There could have been some constants added on there. We don't really know. That gets lost in the differentiation. So let's go over some notation. If I wanted you to find the antiderivative of a expression, here's how I would signify that. And it's an unfortunate use of notation, in my opinion, because to me, antiderivatives are kind of something different than an integral. But as you can see, the integral sign is what tells us we're finding an antiderivative. So if I want to find the antiderivative of, say, I don't know, 4x cubed minus 5x plus 4 over x squared dx with respect to x, then we can just use the power rule term by term, or the I guess inverse power rule, I suppose you could say. So anyway, so if we start with our x to the third, we add 1, that makes x to the fourth. So then we'll divide by our new exponent. So we'll get 4 over 4. Here we have x to the 1, so we add 1, then we'll divide by the new exponent. Now this might be a little bit confusing, but remember we could write this as 4x to the negative 2. And so we do it the same way. Let's just add 1 to the exponent, which would make 4x to the negative 1, divide by the new exponent, so actually we'll have 4 over negative 1. Don't forget that we might have had a constant on here that we don't know about, right? That gets lost in translation, so we'll just go ahead and add our plus c before we forget about it. And let's go ahead and simplify. So 4 over 4 is just a 1. 5 halves, not much to do there. Let's just go ahead and make that minus 4. Actually, let's do this. Let's make that minus 4 over x, right? Because x to the negative 1 be down in the denominator, plus c. So there we go. So that's how we would find that antiderivative. So notice how I rewrote this term here. That's kind of important because just like with differentiation, at first you think the power rule, that may not be too useful, how many things are polynomials, but you can get a lot of mileage out of it because anything like so you can write as a negative exponent. And think about this, if I'm doing the antiderivative of, say, the cube root of x, if I rewrite that real quick and make that x to the 1/3, all of a sudden I can use the power rule again, right? I could just add 1 to that. That would make it x to the 4/3. I divide by my new exponent, which is to say I'll multiply by the reciprocal. Don't forget to add plus c. So we can handle radicals that way. We can handle rational functions that way. Or I should say maybe reciprocal functions that way. And we can handle polynomials that way. So we really do get a lot of mileage out of this inverse power rule. And so let's go ahead and do let's go ahead and do a definite integral using the inverse power rule. So what if I wanted to find the area under the curve from negative 1 to 3 of, let's say, 1/3 x squared minus 4x plus 5 dx. How do I do that? Well, I'm using the fundamental theorem of calculus here. So first I find my antiderivative, and so let's go ahead and do that. Add 1 to the exponent, divide by the new would give me x cubed, right? Because I'd have 3 over 3, they cancel. Add 1 to that exponent, which would give me x squared, divide by the new exponent, and I'll just have 4 over 2. And then I'll have 5x plus c, and we're going to evaluate that from 3 to negative 1. From negative 1 to 3, I suppose. And so all that really means to do is we'll plug in 3 to our expression. I know this plus c looks weird here, but it's all going to work out in the end. And then we'll plug in negative 1 to our expression. No, I'm running out of space and running out of time. Just don't forget that this entire expression is being subtracted off. And then we're just evaluating. This was a cube, by the way. So that's going to be 27 minus 9, 18, plus 15, plus c. And now let's see here. That's going to be minus, well, negative 1. So actually it's going to be plus 1. Minus 2. Oh, I'm sorry. that should be a square. So actually that's going to be plus 2. That'll be plus 5 minus c. I was just distributing that negative, oh no, across the way there. And so let's go ahead and see what we can simplify. C's cancel. Fun fact, C's will always cancel. So really, if we're doing a definite integral by using the power rule here, we really don't need to include the plus C because they're always going to cancel. But either way, if you forget to not include it, they'll just cancel out. So that's going to be 27 minus 3 plus 3 plus 5. So it looks like to me I'm going to get 33 would be the answer to that definite integral.